All right, so we've talked a lot about this enthalpy change and what it actually means for either a chemical or a physical system, but how do you actually measure it? So the actual laboratory tool, which you'll see in building or designing a heat pack lab, is this thing called a calorimeter. The process by measuring heat flow in a chemical or physical system is calorimetry. So this picture that I have here is an example of a calorimeter. The purpose of a calorimeter, or what a calorimeter is a device that allows the measurement of heat transfer during a chemical reaction. And you know, this is a generic version, but you could really imagine this with a simple coffee cup, which is what you do in a lab, in a Chem 107 lab. Or you can have a research grade one, which is really, really nice. But the idea is this thing is just a closed vessel that's really well insulated. So imagine like a thermos, where a thermos, you know, has a double wall typically that's evacuated, meaning there's no gas in there to transfer heat through. So whatever heat is being generated in the system, it's not being lost outward. So you've essentially got a really, really nice thermos. All the heat produced in the chemical reaction inside, so there's a chemical reaction that you control inside, meaning you put in what you want, whatever the chemical system is, and then you measure the temperature. And so in a calorimetry experiment, you are measuring a temperature change, or a delta T, which is really, as we know now, a proxy for heat, and we're going to use that to get to the delta H, or the change in enthalpy of the system. So we need to learn how to actually do this calculation. So the tool to collect this data, the temperature change for a chemical reaction, is a calorimeter. So we'll talk about this in a second. But how do we do this? How do we go from the temperature that we change and we measure to computing the enthalpy of a particular reaction? So in order to translate that experimental measurement via calorimetry, this delta T, or temperature change, to a chemical concept, delta H here, we need to use this sort of conversion factor, which is really a calibration factor, called heat capacity. And the heat capacity is the amount of heat required to raise the temperature of a particular substance. And so the heat capacity is unique to the substance. It's different for all different things. Everything has a different heat capacity. And it's defined in an expression where C is the heat capacity of that substance, which is the amount of heat, Q, amount of heat transferred per temperature change. So delta T, temp change, where this is going to be whatever the final temperature is minus the initial temperature of that object. We could rearrange this expression and we could write this out as the heat absorbed or transferred in the system is going to be whatever the heat capacity of that substance is. So that's the heat capacity of that particular substance times whatever the temperature change of the system was. There's two common ways to report the heat capacity of a particular substance. Both are correct. Both are just useful in different ways. So we could have the specific heat of a substance, which is the heat to raise the temp of a substance by 1 degree C for every 1 gram, or per 1 gram of that substance or stuff. So the specific heat is heat required to raise whatever that stuff is by 1 degree for every gram of it. We could also think about things from a molar heat capacity perspective, which in that case is the amount of heat, very similarly, heat to raise temp by 1 degree, temp by 1 degree C for 1 mole of the stuff. So depending on whether or not we're working in grams of a substance or moles of a substance, both can be useful. That's just a slight unit change based on the molecular weight or formula of that compound. I think heat capacity is actually a pretty intuitive concept for most of you. I like to use the example of sort of cookware. Whether you've cooked with these things or not, I think you can think intuitively about the amount of heat these things can absorb or how much heat is required to get these things to heat up. So if you have this really heavy-duty cast iron, if you've ever held one of these pans, they're 5 to 10 pounds. They're quite heavy. And you know that if you put this on a flame or some sort of heat source, it takes quite a bit of time to get the temperature to actually increase in this pan. In contrast, if you have a thin aluminum pan like this and you supply the same heat source, almost instantly you have the pan at the temperature of the flame. So what's the difference in these two substances? Well, this one on the left, the cast iron, has a much higher specific heat or heat capacity, meaning it takes a lot more heat to raise the temperature of this pan by 1 degree for every gram of it than does this thin aluminum pan. And so all substances are this way. And so the heat capacity here is really our tool. If we know the heat capacity of a substance, then we can use that in calorimetry to measure ultimately what the heat flow of the system is. Meaning if we know how much an object should raise or lower in temperature based on how much of it we have, and we put a known amount into our calorimeter, then we can use the temperature change to equate that to a Q, heat, which we then can say for systems at constant pressure, which we're always dealing with, that's the same as delta H. That's really the utility of calorimetry. So when we have a substance with a known specific heat, which again is the amount of heat in joules or kilojoules required to raise the temperature by 1 degree per gram, that unit then is going to be joules per gram per degree C. That's going to be specific heat. If we then know the mass in grams of that substance and the temperature in degrees Celsius, what that allows us to do is compute the overall heat transferred to that system in joules. That's calorimetry. And calorimeter is the specific design of the experiment that limits the interaction or interference of the surroundings so we don't lose heat from the system. We keep it and we measure it and we don't lose it. That's the purpose of using a thermos. So let's do a quick example here where we're not doing calorimetry per se. This is a step before we get to calorimetry, but we're using some physical data to actually measure what the heat capacity of a substance is, in this case lead. So the question says, what is the specific heat, or C, of PB solids, lead solid, in units of joules per gram Celsius if it takes 97.2 joules to raise the temperature of a 75.0 gram block of lead by exactly 10.0 degrees Celsius. And the second question then is to convert that specific heat to a molar heat capacity. So let's start with the first question here. So the first question is to just evaluate what is the specific heat. So remember, specific heat is the joules of heat required to raise the temperature for every degree C for every gram of solid, right? And so we know that that's the definition of this specific heat. So we could rearrange the equation we had before, or we could think about it intuitively like this. So remember, the equation before was heat is equal to mc times delta T. So if we rearrange this for C, this would be Q over m delta T. What are the units of each of those? Well, Q is joules, m is grams, delta T is degrees C, which is exactly what we have written up here, just based on the definition of this thing. So either way, this is what the specific heat is. So that means we need the heat, which was 97.2 joules. That was required to raise the temperature of a 75.0 gram block by 10 degrees C. So if we compute this, it's going to give us a value of 0.1296, and that's going to be in joules per gram degree C. If we want to keep to sig figs here, I think we've got 3. So this would actually probably best be written as 1.30 times 10 to the minus 1 joule per gram per degree C. So this would be the specific heat capacity of lead, and that's a constant. So once we know that for lead, it doesn't matter if we have a 75-gram block or a 1,000,000-ton slab of lead. The heat capacity is still going to be 0.13 joules for every gram of it to get it to raise up by 1 degree C. So if we want to convert that to molar heat capacity, all we need to do is convert the 75 grams of lead to moles of lead, and everything else is the same. So let's say 75 grams of lead, that's going to be equal to 0.36197 moles of lead, so just using the atomic weight of lead from the periodic table. And then the equation for C here, I'll put maybe subscript little m for molar heat capacity compared with specific heat up here. So for the molar, it's exactly the same, but instead of per gram, it's per mole. And so I have N here just to signify, put the moles here. So I'm just substituting that value in, 0.36197 in here. Our units then are going to be in joule per mole per C, per 1 degree C, which is 26.9. Alright, so we've got a full example here, which is going to require us to use a lot of the knowledge that we've curated so far in this class, some stoichiometry, some understanding of chemical reaction types in aqueous solutions, and then obviously thermochemistry and calorimetry. So we're going to try to compute the change in enthalpy for a calorimetry experiment, and specifically the reaction we're thinking about trying to compute is for the reaction of silver plus and chloride to produce silver chloride as a precipitate. And so hopefully you remember from back in chapter 4-ish, 3 and 4, we talk about precipitation reactions. We learned, it's one of the solubility rules, that silver is soluble with lots of stuff, but it's not soluble with halides. So when you have chloride and silver mixed together, you're going to produce silver chloride as a precipitate. So the question gives us sort of an experiment that we need to consider. So you've got 10 milliliters of 1 molar silver nitrate, and we're going to add that to an equivalent volume, 10 milliliters of 7 molar sodium chloride. And we're going to do that 25 C inside of a calorimeter. We know that this white precipitate forms, that's silver chloride, and that we measure a final temp of 32.6 centigrade. We have water in the system. Obviously, these are solutions of water, salt and water, and the specific heat of the water is 4.18 joules per gram of water per degree Celsius temperature change. And we can assume the density of the final mixture is a gram per mil. And we also can assume that the calorimeter absorbs no heat. And I'll also add another assumption, which is that this is all under constant pressure. So we're doing this in a lab, and we're assuming the atmospheric pressure is constant, which is almost always going to be the case. So how do we approach this? And again, we want to calculate the delta H of the reaction per mole of silver chloride. Okay, as always, I like to start by drawing out what the experiment is being described, because it helps me sort of contextualize what's happening and how I should move forward. So I always recommend this. So what I drew up was the calorimeter in the center. So that's this big square thing here, and it's got a thermometer in it. That's what a calorimeter is, and it's contained. So it's essentially a thermos. And we're pouring 2 beakers of stuff in there. We got the beaker on the left, which is 10 mils of 1 molar silver ion. I'm just writing out silver ion because we're adding silver nitrate, but we know that if we write a net ionic equation for this, the nitrate's always soluble. And we also are told that the reaction is silver plus chloride minus. So we know the silver is coming from the silver nitrate. Similarly, on the right side, we've got 10 mils of a 7 molar chloride solution. Again, sodium is always soluble, and we also know this is just the chloride that's in the reaction. So we've got these two things, we're mixing them together, which means we have a total volume in our calorimeter of 20 milliliters. So remember, we're trying to figure out what is the heat that's that's flowing from this system per mole of silver chloride. We also know that the temperature change here is going to be our 32.6 minus whatever we started with, which was 25 degrees C, which in this case gives us a delta T 12.6. Let's see, 12.6 degrees C. So let's start by writing out the expression for heat, because that's what we're ultimately trying to compute here, right? We know that for a constant pressure system, which is everything we're going to deal with, the delta H, the enthalpy change for the system, it is the same as Q under constant pressure conditions. So we're trying to compute this. This is what we want to know. But ultimately what we can measure is heat in a calorimeter, and we use, how do we get heat? Well, we actually measure temperature. And we know that the heat change is going to be equal to the mass of the substance times its specific heat times whatever the delta T is that we measured in the calorimetry experiment. So let's figure out what we know. Do we know Q? No, not yet. That's what we need to compute, because that will tell us what the delta H is. Do we know the mass of the solution? Well, we could probably figure it out, right? Because we know its total volume is 20 mils, and we're told that the density of that mixture is a gram per mil. So we know if we've got 20 mils of it, and every mil weighs a gram, right? So yeah, we actually could figure that out pretty quickly. We could say, well, if we've got 20 mils, that's the same as 20 grams. We can do that dimensionally too, but I think you can do that on your own. So we'll say that's 20.0 grams. So yes, we've got that. What about the specific heat of the substance? Well, it says assume specific heat of water is this. In this case, and this is almost always going to be true, we are going to use water as the sort of medium by which the temperature change occurs. Even though we're mixing all these other things, water is still the dominant stuff in solution. So this assumption is probably going to lead to some error, some systematic error in our measurement, but almost always we're going to negate that, and we're, instead of saying that we're dealing with the specific heat of this whole solution, which contains silver, nitrate, sodium, and chloride, we're just going to assume it's pure water, because water has a really well-known specific heat capacity of 4.18 joules per gram per Celsius. So in this case, yeah, we know the specific heat. Do we know the delta T? Yeah, we just figured it out. It's 12.6. So it's actually easier than we think to get to the heat, or the delta, or the Q of the system. So let's calculate Q first. So Q at constant pressure is going to be equal to the mass of this thing, which is 20.0 grams, times its specific heat of water, 4.18 joules per gram per degree C. Remember, that's the thing that's changing temperature, is the water of the solution, and we know that because we're given that, times the temperature change, which is 12.6 degrees C. So we can compute that out, and that gives us 6.4 times 10 to the second joules. Quick aside here, why did I only keep 2 sig figs here? Because it looks like I've got 3 here, 3 here, and 3 here. The answer is that's true, but this digit here, it comes from the fact that the subtraction step here, and I actually made a mistake in the back, so I just erased this, but this delta here should actually be 7.6 for the delta T here, so I apologize for that. I've updated that here. That's 7.6 as well. Remember, this is a subtraction step, so the sig fig rules for this are preserve the least number of digits in the decimal place. In this case, it's 1. So that gives us actually only 2 total sig figs in this number. So we know 2 total sig figs in this number, which means that we can only know this to 2 total sig figs as well. So this is the heat released in joules. but we need to get to delta H, which in terms of per mole, that means we need to figure out how many moles of the silver chloride were actually formed. That requires us to think back to this idea of limiting reagents, because we're adding 1 molar, actually we do it over here, we're adding 1 molar of silver and 10 milliliters of it, and we're adding 10 mils of a 7 molar solution of chloride. These two things are reacting 1 to 1, so it's pretty obvious here which one's going to run out first, because the volumes are the same, but we've got a 7 times more concentrated chloride solution. So that means this is going to be the limiting reagent. I did that sort of by eye, but you could just do this in the normal way that you know how, which is just compute the yield of silver chloride for both scenarios as limiting reactant and figure out which one has the least. So let's use the 10 mils of 1 molar silver to compute how much silver chloride was produced in this reaction, knowing that this heat was liberated during this reaction. If we know then how many moles of silver chloride are produced, then we could say that this amount of heat was produced per that number of moles, which would give us a kilojoule per mole relationship. So let's say we have, let's figure out moles of silver plus, so we know that's the limiting reagent. Set that up with dimensional analysis. We start with the original concentration of the silver ion, which we know to be 1.00 molar coming from the problem itself. I just wrote that as 1 per 1,000 mils. I skipped that conversion between mils and liters. We've got 10 mils of this stuff, and then we know that for every mole of silver that reacted as the limiting reagent, that produced 1 mole of silver chloride. So this is essentially just a yield. So we yielded 0.0100 moles of silver plus, so the final step here would be to divide these two, the heat divided by the moles, and that would equate to 64 kilojoules per mole of silver chloride. And that is the final answer of the example.